Spring 1953, Korean Peninsula. 12 B-29 superfortresses climbed to 15,000 feet, carrying a simple mission: destroy one railroad bridge spanning the Yalu River. Each bomber hauled 2,500-pound general-purpose bombs. Do the math, that's 240 bombs, 120,000 pounds of high explosive, aimed at a structure 600 feet long and 40 feet wide. The bombardiers peered through their Norden bomb sights, instruments that cost $8,000 each and promised precision from altitude. They released on the lead aircraft's signal. 240 bombs tumbled earthward, fins stabilizing their fall, following ballistic trajectories calculated before takeoff. Wind at altitude pushed them east. Crosswinds at 8,000 feet nudged them west. Temperature variations changed air density, each variable compounded. When the smoke cleared, the bridge stood intact. Craters pockmarked both riverbanks. One span showed minor damage. The train tracks? Operational within 6 hours. This wasn't incompetence. This was physics. A Mark 82 bomb, dropped from 15,000 feet, follows a parabolic arc spanning nearly 3 miles horizontally. Release timing errors of 1/10 of a second translate to 100-foot misses on the ground. Aircraft speed variations of 5 knots mean 50-foot deviations. Wind shear, air pressure, even the bomb's temperature. Everything mattered, and nothing could be controlled once the weapon left the rack. The Air Force called it Circular Error Probable, or CEP. Their best crews, perfect conditions, achieved 400-foot CP. That meant half your bombs landed within a 400-foot radius of the aim point. The other half, anywhere beyond. Hitting a bridge required not precision, but saturation. Drop enough ordnance and probability takes over. Korea saw this pattern repeat endlessly. The Hwacheon Dam required 140 sorties. The Toksin Dam absorbed 1/100 bombs before failing. Each mission meant fuel burned, crews risked, aircraft lost. And the targets? Often operational again within days. By 1965, Vietnam made the problem impossible to ignore. The Thanh Hoa Bridge, nicknamed Dragon's Jaw, carried North Vietnamese supplies south along Route 1. It stretched 540 feet across the Songma River, built with Vietnamese and Chinese steel, anchored in massive concrete abutments. Between April 1965 and December 1972, the Air Force flew 871 sorties against this single structure. They dropped thousands of bombs, lost 11 aircraft, and watched the bridge survive. Each failed mission cost $10 million in munitions and aircraft exposure. More critically, each mission risked 8 to 12 American aircrew. The tactical absurdity frustrated everyone from cockpit to Pentagon. Pilots knew they'd hit the target if they could just put the bomb exactly on it. But exactly didn't exist in their arsenal. The technology gap was glaring. America could build computers that filled rooms, rockets that reached orbit, submarines that stayed submerged for months. Yet the fundamental bombing technology differed little from 1943. You pointed the aircraft, calculated wind and altitude, released on timing, and hoped. The bomb itself had zero intelligence, zero ability to correct course. It was dumb iron obeying gravity. Military planners understood the equation. Precision meant fewer sorties, reduced losses, faster target destruction. They wanted smart weapons desperately. They just didn't know how to build them. Then a quiet engineer from Texas walked into a laboratory with an idea about lasers. Weldon Word didn't look like a revolutionary. Born 1922 in rural Texas, he'd spent his career at Texas Instruments designing electronics for military contracts. Radar components, guidance systems, nothing glamorous. By 1964, he managed a small advanced development group in Dallas, the kind of team companies kept to explore emerging technologies before they became profitable. That year, TI acquired a small laser laboratory. The timing was perfect. Theodore Maiman had demonstrated the first working laser at Hughes Research in 1960, a ruby crystal pumped by a flash lamp, producing a concentrated beam of coherent light. The technology fascinated engineers, but frustrated businessmen. What could you actually do with a laser besides punch holes in razor blades for demonstrations? Word saw something else. He'd been reading Air Force requests for proposals, particularly one from the Armament Development and Test Center at Eglin Air Force Base. They wanted precision guidance for conventional bombs. The requirements seemed impossible. Survive the shock of release, function in combat conditions, cost less than $10,000 per unit, and guide a bomb to within 20 feet of a name point. The existing approaches all failed somewhere. Television guidance required clear visibility and distinctive targets. Infrared seekers couldn't distinguish bridges from rivers. Radar homing worked against ships, but struggled with ground targets. Wire-guided systems limited range to a few thousand feet. Word kept returning to lasers. Coherent light meant you could focus enormous power into a tight beam. Reflect that beam off a target, and you created a distinct point of concentrated energy. A sensor could detect reflected laser light against background clutter with far greater reliability than conventional optics. The wavelength, 6,943 angstroms for ruby lasers, was specific, filterable, unmistakable. The concept crystallized during a February 1965 meeting with his engineering team. Someone mentioned the military's need for target designation. Word sketched on a whiteboard. Aircraft A illuminates the target with a laser. Aircraft B drops a bomb equipped with a seeker head tuned to that laser wavelength. The seeker tracks the reflected light. Control fins adjust the bomb's trajectory. The weapon rides the laser beam straight to the reflected spot. His deputy chief engineer raised the obvious problems. Shock loads during release would destroy delicate optics. Atmospheric conditions would scatter the beam. The seeker would need a wide field of view to acquire the target, then narrow tracking as it approached. And they'd need to do all this with 1960s electronics. No microprocessors, no integrated circuits beyond basic logic gates. Word didn't dismiss these concerns. He assigned each one to a team member with a deadline. TI had experience building rugged military electronics. They understood vibration isolation, thermal management, hermetic sealing. The optics challenge? Talk to the laser division. The wide to narrow field of view problem? Mechanical solution. A lens system that adjusted based on range. The Pentagon's formal request hit Word's desk in March 1965. Project Paveway. Budget: $99,000 for feasibility study. Deadline: 6 months to demonstrate basic concept. The amount was laughable for aerospace development. Boeing spent that much on coffee and engineering notebooks, but it was enough for Word to prove his idea wasn't fantasy. He assembled 8 engineers in a second-floor laboratory. They scrounged surplus bomb fins from Eglin, borrowed seeker components from missile programs, machined guidance vanes in TI's prototype shop. The goal wasn't elegance. It was proof that laser-guided bombs could exist outside theoretical physics papers. By September 1965, they had hardware ready for testing. Not a complete weapon, but enough to demonstrate the principle. Word scheduled the first drop for November at Eglin's range. He was about to make military aviation obsolete. The TI laboratory measured 30 feet by 40 feet, crammed with oscilloscopes, soldering stations, and half-assembled guidance units. Word's team worked 12-hour days through fall 1965, building a seeker head that could survive what no laboratory instrument ever had to endure. The core challenge was optical. Engineer James Pinson designed a 4-inch diameter gallium arsenide detector, sensitive to the ruby laser's 6,943 angstrom wavelength. Behind it sat a series of filters blocking everything else: sunlight, reflections, ground clutter. The detector needed to distinguish one specific frequency of reflected light from every other photon hitting it at 200 miles per hour, but detection meant nothing without control. The seeker fed signals to a guidance computer built around discrete transistors. No integrated circuits existed yet with sufficient radiation hardness. Circuit designer Donald Hess created a comparator system weighing just 11 pounds, that could process seeker inputs and command fin movements 20 times per second. The control surfaces were Word's elegant solution to a brutal problem. 4 bang-bang fins mounted in the bomb's tail section, not proportional control, binary. Fin up or fin down, hard stop to hard stop, actuated by nitrogen gas cartridges. Crude but reliable, and fast enough to make corrections throughout the bomb's fall. November 18, 1965, first live test at Eglins Range. They mounted the seeker assembly on a standard Mark 82 500-pound bomb, attached the fin kit, loaded it onto an F-4 Phantom. On the ground, technicians aimed a ground-based laser designator at a plywood target 8,000 feet downrange. Word watched from the control bunker as the Phantom climbed to 15,000 feet. The pilot called, "Ready." The laser operator triggered his designator, painting the plywood with invisible light. The Phantom rolled in, released. For 23 seconds, the bomb fell. Inside its nose, the seeker tracked the reflected laser spot. The guidance computer processed position errors. Nitrogen gas slammed control fins left, right, up, down. Small corrections, continuous adjustments, the bomb flying itself toward reflected photons. Impact. 18 feet from the laser spot. 18 feet. After a 3-mile fall, the team erupted in cheers. Word just nodded and called for the next test. They flew 17 more drops over the next month. Average miss distance, 23 feet. Conventional bombs averaged 400 feet on a good day. Word's prototype achieved better than 90% improvement with hardware built in 6 months for under $100,000. But the real validation came during Test 14. The laser operator deliberately moved his designator mid-flight, slewing the spot 200 feet left. The bomb followed. Shifted right. The bomb corrected. This wasn't just precision. It was control. You could move the impact point after release, guide the bomb to different targets, compensate for errors. The implications hit immediately. A single aircraft could destroy a bridge instead of needing 50. Pilots could release from higher altitude outside anti-aircraft range. Missions requiring 100 sorties could be accomplished in 1, and civilian casualties from stray bombs nearly eliminated. Air Force observers filled notebooks. They'd seen guided weapons before. Expensive, fragile, unreliable. This was different. The seeker had no moving parts except the fins. The electronics were solid state. The cost? Word estimated $3,000 per guidance kit in production quantities, less than the fuel burned on a single failed conventional strike. Word's team celebrated that night, knowing they'd proven the concept. What they didn't anticipate was the institutional resistance about to hit them. The Pentagon had 100 reasons why laser-guided bombs wouldn't work in combat. Word would need to answer every single one. The briefing room at Wright-Patterson Air Force Base held 40 officers, March 1966. Word stood at the front with his test data, prepared to demonstrate why Paveway would revolutionize air warfare. He got 15 minutes before the questions turned hostile. A colonel from Tactical Air Command went first. "Mr. Word, your Nevada tests used a ground-based laser designator on a static target under clear skies. In Vietnam, we're hitting targets through jungle canopy in monsoon conditions. Your laser beam scatters in humidity, gets blocked by vegetation, and becomes useless in clouds. How do you address that?" Word acknowledged the point. Atmospheric attenuation was real. Water vapor, dust, and smoke all degraded laser transmission. But the math still worked. Even with 30% power loss through humid air, the seeker could track reflected energy from 15,000 feet. Jungle canopy. Designate from angles that clear the foliage, or use bridges, buildings, concrete structures as targets. The colonel wasn't satisfied. And who operates this designator? You need someone on the ground forward of enemy lines, or a second aircraft maintaining position while the striker makes his run. That's double the exposure, double the risk. Another officer jumped in. The guidance kit costs $3,000 per unit, you said. We're dropping 800 bombs daily in Vietnam. That's $2.4 million per day in guidance kits alone. Congress will never fund it. Word countered with sortie math. One Paveway-equipped F-4 could accomplish what previously required 50 conventional strikes. Calculate the fuel, maintenance, and aircraft exposure costs. The guidance kit paid for itself if it eliminated even 5 conventional sorties. The room stayed skeptical. A maintenance officer raised the practical concern that worried Word most. Your seeker has a 4-inch optical window exposed to airflow at 500 knots. One raindrop at that speed hits with the force of a bullet. The optics crack, you get debris ingestion. The whole system fails. We can't maintain this in field conditions. This was legitimate. Laboratory tests didn't replicate typhoons or dust storms. The seeker window needed hydrophobic coating, hardened glass, redundant seals. Word's team was working on it, but he couldn't promise combat-ready reliability yet. Then came the institutional resistance disguised as tactical concern. A brigadier general who'd flown 200 missions in World War II leaned back. Gentlemen, we've been bombing successfully since 1918. We know what works. More aircraft, more bombs, saturation strikes. This laser business sounds like Hughes Aircraft selling us another expensive science project that breaks in combat. The Falcon missile promised revolution. The Corvus promised revolution. They all ended up hangar queens. Word kept his voice level. General, with respect, we're losing aircraft because we need multiple passes to hit targets. Thanh Hoa Bridge alone has cost 11 aircraft and 871 sorties without success. Paveway could destroy it in one mission with one aircraft. The general smiled. In Nevada, maybe. In combat? I'll believe it when I see it. That became the consensus. Interesting technology, promising test results, but unproven in combat conditions. The Pentagon authorized continued development, a modest $2 million for 1967. Enough to keep the program alive, not enough to scale production. Word left Wright-Patterson understanding the real obstacle wasn't technical, it was psychological. Generals who'd won wars with mass bombing couldn't imagine precision replacing tonnage. He needed combat results, not laboratory data. Vietnam would provide that proof sooner than anyone expected. Word returned to Dallas knowing laboratory perfection meant nothing without operational proof. Spring 1967, the Air Force authorized expanded testing at Eglin Air Force Base in Florida. Not the cramped Nevada facility, but Eglin's massive range complex with realistic tactical scenarios. The test director, Colonel Joseph Davis Jr., designed a program that mimicked Vietnam conditions. They built replica targets, reinforced concrete bridge sections, camouflaged bunkers, moving truck convoys. The goal wasn't just hitting stationary plywood anymore. It was demonstrating Paveway could destroy hardened military infrastructure under tactical constraints. Test Series 1. Bridge spans. Engineers constructed a steel truss bridge identical to those carrying North Vietnamese supply routes. Conventional bombing baseline came first. 6 F-4 Phantoms, 12 bombs each, released from 10,000 feet using standard Norden bomb sights. 72 bombs, expert crews, perfect weather. Results: 3 hits on the bridge structure, causing minor damage. Average miss distance, 420 feet. 69 bombs cratered empty rangeland. The math was brutal. You'd need 200 bombs to guarantee bridge destruction through probability alone. Next run, Paveway. Single F-4, single bomb, same altitude. A ground observer designated the bridge's center span with a portable laser unit weighing 40 pounds. The Phantom released. 22 seconds later, the bomb struck the center span's support column. Impact distance from laser spot? 9 feet. The span collapsed. They repeated the test 18 times over 3 weeks. Average Paveway accuracy, 12.7 feet. 0 misses beyond 30 feet. Each bomb hit the designated structure, not the area around it, the actual target. Colonel Davis recorded every detail. Cost comparison showed one Paveway strike equaled 35 conventional bombs in destructive probability. Pilot exposure time decreased by 90%, one pass versus multiple runs. Collateral damage radius shrank from 800 feet to 50 feet. Test Series 2 addressed the weather concerns. They bombed through simulated smoke using oil fires upwind of targets. The laser penetrated smoke more effectively than anticipated. Infrared wavelengths passed through particulates that blocked visible light. Hit probability decreased only 15% in heavy smoke. Rain testing proved more problematic. Heavy precipitation scattered the laser beam, degrading designation quality. But the data showed acceptable performance in light to moderate rain, conditions covering 80% of Vietnam's weather. Only in typhoon conditions did the system fail completely. Same conditions grounding conventional bombing anyway. The moving target tests surprised everyone. They mounted targets on flatbed trucks traveling 30 miles per hour. The laser operator tracked the moving vehicle while the bomb fell. Paveway adjusted continuously, following the laser spot's movement. 7 out of 9 tests achieved direct hits on moving targets. Conventional bombing couldn't touch moving vehicles. You aimed where they'd be, hoped they didn't change speed. Word's team made refinements after each test series. They added a backup battery when one unit lost power mid-flight, strengthened the optical window after a bird strike cracked the glass, improved the fin actuators to handle faster correction rates. Each modification came from operational data, not theory. By August 1967, Eglin had accumulated 127 Paveway drops. Success rate, 94% within 30 feet of designation point. Conventional bombing success rate at the same criteria, 3%. The statistical case was irrefutable. Colonel Davis submitted his final report to Tactical Air Command with a recommendation: immediate operational deployment to Vietnam. The war offered perfect testing conditions: diverse targets, contested airspace, desperate need for precision. Headquarters approved limited combat trials. 40 Paveway kits shipped to Ubon Royal Thai Air Force Base in October 1967. Word wasn't invited. Civilian contractors didn't deploy to combat zones. He'd done everything possible in peacetime. Now combat would render the final verdict. May 13, 1972. The Thanh Hoa Bridge had survived 7 years of American bombing. Since April 1965, it had absorbed more ordnance than any structure in military history. 871 sorties, thousands of bombs, 11 aircraft lost. Engineers kept repairing it. Supplies kept flowing south. The bridge earned its nickname honestly. Dragon's Jaw was 540 feet of Vietnamese defiance. Steel trusses anchored in concrete abutments, thick as battleship armor. Soviet engineers had supervised construction, using techniques designed to withstand bombing. The superstructure could lose entire sections and remain functional. Approaches on both sides featured anti-aircraft batteries, 37mm and 57mm guns, SA-2 surface-to-air missiles, and enough small arms fire to shred aluminum. Traditional bombing hadn't worked. Precision hadn't existed. You saturated the target area and hoped. The Air Force tried everything: low-level attacks that cost aircraft, high-altitude runs that missed completely, even experimental weapons like the AGM-62 Walleye TV-guided bomb that performed poorly in combat conditions. Then Paveway arrived in theater. 12 F-4 Phantom IIs from the 8th Tactical Fighter Wing carried the laser-guided bombs, supported by Wild Weasel aircraft for SAM suppression, and F-4s equipped with laser designators. Mission Commander Colonel Carl Miller briefed his crews on the approach: 4 ship elements, staggered release times, all bombs guided to the same designation points on the bridge's support structures. The formation launched from Ubon at 06:30 hours. They crossed into North Vietnam at 20,000 feet, staying above the worst of the anti-aircraft fire. The SA-2 sites lit up immediately, Soviet-built missiles arcing upward trailing white smoke. The wild weasels countered with AGM-45 Shrike anti-radiation missiles, suppressing the SAM batteries long enough for the strikers to set up. The first element rolled in at 0847. The lead F-4 carrying the laser designator descended to 15,000 feet, began illuminating the western abutment. His wingman called "captured." Seeker locked on the reflected laser energy. Release at 14,000 feet, diving at 30 degrees. The 2,000-pound bomb with Paveway guidance kit fell free. Fins deploying, Seeker tracking. Impact, direct hit on the abutment, penetrating 6 feet of reinforced concrete before detonation. The structure shuddered but held. That was expected. One bomb couldn't collapse it. The second element attacked the eastern span 90 seconds later. Same procedure. Designator painted the target, striker released on the laser spot. Another direct hit, this time on a primary support truss. Steel buckled. The roadway sagged 3 feet. Third and fourth elements followed within minutes, each bomb guided to specific structural points. The bridge's defenses never adapted. Their anti-aircraft guns aimed where conventional bombers had attacked before, higher and less precise. The Paveway strikers came in different angles, different altitudes, stayed in the envelope just long enough to release. 14 bombs total. 12 direct hits on designated points. 2 missed by less than 20 feet due to designator tracking errors. The cumulative damage was catastrophic. The western span collapsed into the Songma River at 0903. The eastern approach showed severe structural failure. The center span, weakened by successive hits on support trusses, sagged beyond repair. By 1,000 hours, the Dragon's jaw was broken, not damaged, destroyed. Reconnaissance photos confirmed what crews reported. The bridge was impassable, both vehicle and rail traffic stopped. One mission, 14 bombs, no American aircraft lost. Word received the after-action report in Dallas 3 days later. 7 years and 871 failed sorties erased in 30 minutes. The Pentagon didn't celebrate Thanh Hoa's destruction with press conferences. They issued procurement orders. Within 2 weeks of the May 13th strike, Tactical Air Command requested 2,000 additional Paveway kits for immediate deployment. By June 1972, that number jumped to 5,000. The institutional resistance that had plagued Word for 5 years evaporated in 30 minutes of combat footage. Texas Instruments' production facility in Dallas went from prototype assembly to wartime manufacturing. The team that had hand-built guidance kits in a second-floor laboratory now supervised 3 shifts, running 24 hours daily. Machinists fabricated seeker housings. Technicians assembled circuit boards. Quality control tested every unit to mil-spec standards before shipping to Southeast Asia. The manufacturing challenge was scaling precision. Each seeker required optical alignment, accurate to 1,000th of an inch. The detector assembly needed hermetic sealing. Any moisture, ingress, degraded performance. Control fin actuators underwent vibration testing, simulating release shock loads. Word's original $3,000 cost estimate held, but only through volume production. By late 1972, TI delivered guidance kits at $2,800 each, with quality exceeding the hand-built prototypes. Combat usage statistics told the adoption story. In 1968, the Air Force dropped 28 laser-guided bombs in Vietnam, experimental use only. 1969 saw 156 Paveway strikes as more squadrons received equipment. 1970, 782 missions. Then Thanh Hoa happened, and 1972 exploded to 10,908 laser-guided bombs dropped in combat. The tactical applications expanded beyond bridges. Paveway destroyed North Vietnamese petroleum storage facilities that conventional bombing had failed to ignite. Precision strikes on tank farms put bombs inside containment walls instead of cratering surrounding dirt. The Paul Doomer Bridge in Hanoi, another heavily defended target, fell to Paveway strikes in October 1972 after surviving 106 conventional attacks. Cave complexes hiding supply depots received direct hits on entrance tunnels, collapsing them with single bombs instead of requiring carpet bombing. aircraft survival rates improved dramatically. Pre-Paveway missions against defended targets averaged 8 to 12 aircraft sorties, with a 2% loss rate per mission. Paveway strikes required 1 to 4 aircraft with losses below 0.3%. Pilots stayed above effective ADA range, released from safer altitudes, and departed immediately instead of making multiple passes. The cost analysis became impossible to argue against. Thanh Hoa alone illustrated the mathematics: 7 years of conventional bombing, $10 million in munitions, 11 aircraft lost valued at $2 million each, 22 aircrew casualties. Total cost, $32 million to fail. The Paveway mission, 14 bombs at $2,800 per guidance kit, plus bomb bodies. Total hardware, cost $67,200. Success on first attempt. Even accounting for support aircraft and mission planning, the Paveway strike cost under $500,000. Multiply that across hundreds of targets, and the Pentagon's reluctance became financial stupidity. Every precision strike eliminated sorties, reduced losses, shortened the war's bombing campaign. Generals who dismissed Word's concept in 1966 now demanded Paveway inventory for their squadrons. By 1973, laser-guided bombs had transitioned from experimental to standard issue. F-4 Phantoms deployed with Paveway capability as baseline equipment. Training pipelines included laser designation procedures. Munitions planning assumed precision weapons for any hardened target. The transformation was complete. Smart bombs weren't future technology anymore. They were present reality. Word's team at TI had delivered 24,000 guidance kits by war's end. More importantly, they'd established the architecture every subsequent precision weapon would follow. Sensor, processor, actuator, all integrated into a package that worked under combat conditions. The revolution Word, sketched on a whiteboard in 1965, had become doctrine. What happened next would prove even more transformative. Word's Paveway established a template that defense contractors worldwide rushed to copy. The fundamental architecture, sensor detecting target, computer processing corrections, actuators adjusting trajectory, became the blueprint for every precision weapon developed afterward. But the real revolution came when engineers asked, what if guidance didn't require an external laser? The global positioning system changed everything. GPS, fully operational by 1993, provided position accuracy within 30 feet anywhere on Earth. Engineers at Boeing realized you could replace Word's laser seeker with a GPS receiver. The bomb would know where it was, know where the target coordinates were, and guide itself to eliminate the difference. No designator needed, no line of sight required. The target could be pre-programmed before takeoff. The result was JDAM, Joint Direct Attack Munition. First deployed in 1997, JDAM bolted a $25,000 guidance kit onto standard Mark 82, 83, or 84 bombs, identical to what Word had done with Paveway 30 years earlier. The kit included a GPS receiver, inertial navigation system, and tail fin assembly with actuators. Release the bomb, and it flew itself to programmed coordinates with 40-foot accuracy. JDAM proved its value immediately. Kosovo, 1999, B-2, Spirit stealth bombers dropped JDAMs through cloud cover that would have prevented laser designation. The bombs hit targets the crews never visually acquired, guided entirely by GPS coordinates uploaded pre-flight. Afghanistan 2001, Special Operations teams transmitted target coordinates via encrypted radio. Within hours, bombers thousands of miles away struck those exact positions with JDAM. But GPS had limitations. Word's laser system didn't. GPS guided you to coordinates, not to a specific vehicle or moving target. For that, the military returned to Word's tracking principle and evolved it. The AGM-114 Hellfire missile, developed in the 1980s, used semi-active laser guidance nearly identical to Paveway's seeker. Launch from a helicopter, illuminate the target with ground or airborne laser. The missile rides the beam to impact. the Army deployed 40,000 Hellfires, using them against tanks, bunkers, and eventually in counter-terrorism operations against individual vehicles. The British developed Paveway-2 and the third variants with improved seekers. France created the AASM Hammer with combined GPS and laser guidance. Israel produced the Griffin laser-guided bomb. Russia reverse-engineered the concept into the KAB-500L. China developed the LS-6 precision guidance kit. Every major military power copied Word's architecture because nothing worked better. The precision revolution fundamentally altered military doctrine. The 1991 Gulf War demonstrated the transformation. Coalition forces dropped 250,000 bombs. Only 7% were precision-guided. But those 7%, primarily Paveway and early GPS weapons, destroyed more strategic targets than the other 93% combined. By 2003 Iraq War, precision weapons comprised 68% of munitions used. The ratio had inverted in 12 years. Aircraft survivability improved accordingly. Modern fighters rarely face sustained anti-aircraft fire. They release precision weapons from standoff distances beyond defensive range. The multi-pass bombing runs that cost aircraft in Vietnam became obsolete. One aircraft, one bomb, one target, mission complete. Word's contribution extended beyond hardware to philosophy. He'd proven that precision was achievable, affordable, and tactically superior. That insight drove 40 years of weapons development. Every engineer working on smart munitions stood on foundations Word laid in a cramped TI laboratory. By the time Word retired from Texas Instruments in 1987, Paveway had spawned an entire industry. Precision guidance wasn't exotic anymore. It was expected. And the engineer who'd convinced skeptical generals that bombs could think had validated something larger. Human ingenuity could make warfare more surgical, more effective, and less wasteful. Weldon Word never sought recognition. He declined interviews, avoided conferences, and spent retirement working in his Dallas workshop building amateur radio equipment. When asked about Paveway's impact, he'd redirect conversation to his engineering team or the Air Force pilots who proved the system in combat. But the numbers told a story Word wouldn't. Between 1968 and 1973, laser-guided bombs achieved a 48% direct hit rate against designated targets in Vietnam. Conventional bombing hit designated aim points less than 5% of the time. That difference wasn't academic. It meant fewer sorties, reduced aircrew exposure, and critically, fewer civilian casualties from stray munitions. The precision Word engineered didn't just make bombing more effective. It made it more humane. The unintended villages hit by conventional bombing errors became rarer with precision weapons. The schools and hospitals destroyed by bombs intended for nearby military targets decreased dramatically. Word's technology couldn't eliminate collateral damage. War guaranteed tragedy, but it reduced the radius of destruction from hundreds of feet to tens of feet. That margin saved lives on both sides. The aircrew survival statistics were equally stark. In the final 2 years of Vietnam bombing campaigns using Paveway extensively, aircraft loss rates dropped by 60% compared to 1968-1970 conventional operations against similar targets. The pilots who returned home, who didn't become POWs or casualties, owed their survival partly to an engineer who'd made precision affordable enough for operational use. Word understood this better than most. His son had served in Vietnam as an F-4 navigator. The personal stakes of reducing required combat sorties weren't theoretical. Every precision strike that eliminated 5 conventional missions meant 5 fewer times someone's son faced anti-aircraft fire. The technology's proliferation brought ethical complications. Word never fully reconciled. Precision weapons made military strikes more politically palatable. Lower collateral damage meant less public opposition to military action. Some argued this made warfare too easy, too clean in planning rooms, far from consequences. Word's response was characteristically pragmatic. If nations chose to fight wars, Shouldn't weapons be as discriminate as physics allowed? By 2020, precision-guided munitions dominated military arsenals worldwide. The U.S. inventory alone contained over 400,000 JDAM kits, thousands of Paveway variants, hundreds of thousands of guided missiles, all descendants of Word's original concept. The global precision weapons market exceeded $30 billion annually. What started in a 200-square-foot laboratory had become the foundation of modern air power. Word died in 2013 at age 91, having lived to see his invention become so fundamental that younger engineers couldn't imagine bombing without guidance. The obituaries were brief, respectful, but didn't capture the magnitude. One engineer had made bombs intelligent. That achievement reshaped military technology more profoundly than any weapon system since radar. The contrast with 1953 was total. Those B-29 crews dropping 240 unguided bombs at a Korean bridge represented the old paradigm, mass application of dumb iron. Hoping probability would prevail, Word's Paveway represented the new reality, precise application of intelligent weapons, ensuring first strike success. The bridge in Korea still stood in 2013, rebuilt after the war. The Dragon's Jaw in Vietnam had been reconstructed too, but the military doctrine that required 871 sorties to fail against a bridge, that was obsolete, destroyed more completely than any target Paveway ever hit. Word's revolution wasn't making bombs smarter, it was proving that precision saved everyone, the pilots, the civilians, even the enemy soldiers who survived, because unnecessary missions never flew. One engineer, one idea, millions of lives altered.